with the continuation of this particular performance metrics and the benchmark, we have, as we have discussed about the clock per cycle. Example, if we go into the previous slide, we have clock per cycle. Regarding the clock per cycle, we have a clock frequency that is measured and ranges between 2 and 3 gigahertz. And with respect to the clock cycle, we have peak arithmetic performance. The peak arithmetic performance will have a certain range between 4 and 12 gigaflops per second per core. How many cores you have for this particular high performance? As high performance will have multiple cores. For each and every core, the peak performance will ranges between 4 to 12 gigaflops per second. Then we have a bandwidth. Bandwidth will get measures in terms of gigabytes per second. The gigabytes per second is nothing but the data which is to and from the cache and the main memory. How much time it will take for the generation, transformation of that particular data, and how much data has been transferred. Now we have gigaflops, gigabytes as a metrics unit value. Then we have cache based microprocessor, as it is difficult, as it is very data centric. Now during the computation process of a particular high performance computing, we can able to manipulate the data items. Now there are certain low benchmarks which helps to compute or analyze the particular operation, which is nothing but a low level benchmark. This tries to go with certain features of the architecture, that is peak performance. Now we have, apart from the performance metrics, we have a vector tree. The vector tree, which is nothing but the nested loop. Like we have some condition, we have some rules which used for performing this particular nested loop. Now we have inner level. Now we have inner level execution of multiple operations in terms of multiply, addition operations on the element of 3 vector, and based on this particular 3 vector, while performing the operation of multiple and addition, we can store the results in terms of a vector. And during the measurement of this particular operation of data transfer between the memory and the arithmetic unit, we can able to measure the performance, where there is a transfer between the data with this application data and the computation. There will be a transferring of data. That transferring of data can be measured in this particular high performance computing. Now we have, apart from this particular application and the computation, here we are considering the arithmetic unit with the main memory. Between the main memory and the arithmetic unit, we have a transferring of data, but during the transferring of data, we have register which is directly attached with the ALU, and L1 cache which is some way far away to the ALU, and L2 which is so far away from the arithmetic unit, but there will be a DRAM notation. We will call it as a DRAM gap, which is there between the L2 and the main memory. And all this L2, L1 register, arithmetic, everything will be fabricated into a single CPU chip. Now regarding the measurement, we have a program how it can be get executed and analyzed. In this we have a double precision dimension which is noted as ABCD, and we have double precision as SC and MFLOPS. Here we have some continuation of loop that is being initialized with I starting from 1 to N. Now we have double precision dimension. We have to assign with those dimension with A, B, C and D with the dimension value of 0, 1, 2 and 3. Now we have to go with the wall time with the get function of S is the double precision of S. We have to get function for the timestamp. Now we have to go with the same continuation of loop with J starting from 1 to R with the inner loop of I is equal to 1 to N, so that we can load and store the particular value with a double precision of ABCD. With A as the store value, we have 3 loads which is nothing but B, C and D, which will continue from I to N data. Now we will be having some system call with a dummy value with ABCD to prevent or check and analyze to prevent the loop interchange. Now we have a call for the wall time which is initiated with E. For the E, we will be having the computation of MFLOPS per second. For determining the MFLOPS per second, we have R and N star 2 into dimension with E minus S with 1 into dimension, which helps to compute the MFLOPS per second. Now we have a inner level, the same that we have seen. Here we have a outer level and inner level. Inner level of this particular operation is B, C and D. And we have a outer level with A which is getting activated to store the stream of data. Now depending on N, we can execute small time and R to measure. But for the outer loop of the trial of R, you see this diagram code, we have a outer loop of R. Outer loop of R, which get executed with a time interval, and it's enough to measure and accurate to measure it in a accurate basis, so that it can measure in terms of a MFLOPS per second. The main aim of this particular mask is how to call a dummy subroutine. By using this dummy subroutine, we can able to prevent the compiler to avoid the overlapping, and also to optimize the execution process. Without this particular call of dummy, the compiler will discover the inner loop and does not depend upon the outer loop of particular J. Outer loop of this particular J. Inner loop of I. So there will be a call with a dummy pool compiler in order to believe that the array may change between the outer loop of this particular iterations. Now we will be having a MFLOPS that is being calculated in that particular previous course, and also we have a clock time which is nothing but a elapsed time, and we can have a get function which is assigned to determine the wall clock timestamp. And also we have a performance graph for this particular vector trail which is obtained for the different generation of cache based microprocessor and the vector system. This is the trial, and this is the code, is the one more code where we will be specifying only with the wall time of this vector trial, where we will be having a system time dot header, and we will be getting the particular function with the wall time with the double function structured with the particular time value, and we will be getting the time of the day. By using the time of the day, we will be able to determine the wall clock time with the double precision with tp.tv.second, and also we will be having a underscore uvv of this particular get and set function. As we are told, we have a performance graph. Here also we will be having a performance graph that has been used for various generation of this particular cache based processor architecture, where here we have taken various standard as NetBurst, Core, Core i7, NEC. These are the various evolution systems related to the particular cache based computer processor architecture and we will be measuring the particular mflops per second based on the n trials starting from 10 to the power 1 to 10 to the power 7. Now we will be having a performance growth with n until some maximum limit followed by sudden drop. That is based on this particular loop value. But based on this particular growth of the performance, there will be steady and constant with the very large loops. But there will be a vector system with standard CPU has to meet with the different domains of the capability. And also we will be having a lower benchmark, which is a powerful tool to get that particular information about the basic capability of the measurement, as we discussed before. We have a lower benchmark, which is a specific tool for the future architecture of the peak performance. Same we have discussed over here also with a lower benchmark as a powerful tool. So with this we will be winding up this particular topic of performance metrics and the benchmark. Thank you everyone.